So continuing with number 93, it says using 2 dice, what's the probability roll a 7 or an 11 the first roll and doubles on the second roll? So if you thought about a little grid maybe, and it says 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. And so when you roll a 1 and a 1, that's a 2, and a 1 and a 2, that's a 3, and et cetera, et cetera. So if you think about this, the ways to get a 7 are going to be right here with 2 things right here. So it's a 6 and a 1. That's hard to read. Oops. It could be a 6 and a 1, a 5 and a 2, a 4 and a 3, a 3 and a 4, a 2 and a 5, or a 1 and a 6. And then or an 11 is a 5 and a 6 or a 6 and a 5. So there are 6 times 6. There's 36 different possibilities in here, and 8 of them give me a 7 or 11 on the first roll. 8 out of the 36. Now, to get a double, it's actually these numbers, double 1, double 2, double 3, double 4, double 5, or double 6. So there are 36 ways to do that. I realize these will reduce. It's easier to explain this way. And since they're independent, because they're rolls of a die, I can just multiply them together. So we get 836 times 636. 0.037. What's the union of 2 events? That's this symbol, whereas the intersection is this. So sometimes we call the union the or, and the intersection the and. If you were thinking about it in terms of a Venn diagram, I'll draw this down here, I guess. This region here is and. That's that part. And then this region here is the or. That's that part. So or is what I call the MasterCard region, and is that little sliver in the middle. I'll come back to number 96. Let me go ahead and do number 97 and 98. It says, give an example of a discrete or a continuous random variable. A very easy continuous one is time, because time just goes continuously. As specific as you want to try to measure it, you can. A discrete random variable is when you're counting anything. So things you count, like, for example, the number of kids in a family, the number of cars on the highway, the number of classes that a student passes, or the number of students in a class. Those are all discrete because you're counting them. Now, number 96 says perform an independence test on smoking and education to show that they are not independent. So I need a little more room right here. Let's work number 96. What I want to see is, for example, is the probability of smoking the same as the probability of smoking given some educational information like less than high school. Less than high school. So if that's true, if those are equal to each other, then they're independent. So we'll go back and look at that question. The probability of smoking was right here. The probability of smoking was 312 out of 825. 312 out of 825. That's this, 312 out of 825. And now I want the probability you smoke given that you went to less than high school. So back here again, it's the probability you smoke, one of these people, but this is a person who did not complete high school. So it's 113 out of 312. 113 out of 312. So that's 113 out of 312. Now maybe you can check the equivalence of those in your head. I'll grab a calculator real quick and go 312 divided by 825, and that's 0.378. And the question is that the same thing as 113 divided by 312? Well, it is not 0.362. So these are not, in fact, equal. And since they are not equal, they are not independent. Or as the question asks, I have now shown that smoking and educational status are not independent events. Continuing with number 99, I've got this distribution. It says make a probability histogram. So down here I've got 0, 1, 2, 3, 4, and this is very low. This is 0.05. That's how tall that is. The next one is 0.28. That's pretty tall. That's here. 0.28. I could put these labels over here on the left axis, that vertical axis. 0.19, that's down a little bit, maybe in here. 0.32, that's way up here, a little higher now. And then 0.16 is like that. There's a good probability distribution. It says what's the probability x is greater than 2? The things that are greater than 2 are just those things. So 32 and 16, that's 48. Probability x is greater than or equal to 2, I need to add that in there also. So this is 0.48 plus 0.19, which is 0.67. Continuing, I've got a uniform distribution. So a uniform distribution, since I'm going to draw it and sketch it anyway, is between 0 and 1. It's the same height the whole way across. And since I know the area of this distribution is 1, the area underneath any density curve is 1, this must also be 1 because this is a rectangle, and to find the area of a rectangle, it's length times width. So since the area is 1 and this number over here is 1, the height has to be 1 also. I could have drawn it like a square. Now it says what's the probability? It's between 0.2 and 0.6. There's 0.2. There's 0.6. One easy way to think about this is just like area of a rectangle. It's this distance, which is 0.4, times the height, which we just said was 1. So the distribution or the probability in that interval is 0.4. The next one says I've got this uniform distribution. Now draw it and sketch it. So here's what we got. Same idea. 1, 1, 1. But now I've included these equal to lines. So whereas over here I drew dotted lines there, I'm going to draw solid lines here. See, there's not really enough room to work in here. But all I've included are those two vertical lines, the one on each end of my shaded rectangle. So the area in this box is unchanged at 0.4. So how do these problems demonstrate a difference between continuous and discrete? A discrete random variable looks something more like what we had on number 99, this. And so whether I include or don't include a vertical bar changes the probability, like on number 100. But on a continuous distribution, like a uniform one, whether I include a vertical line or not at that specific point doesn't change anything. Normal distributions are continuous because they can be any value on that distribution. Expected value is another name for mean. So sometimes we call it E of x and sometimes we call it mu or mu of x. Find the expected value, the variance, and the standard deviation of the grades in problem 99. I'm going to give myself a little more room here to work. So the formulas for expected value and variance are as follows. The formula for expected value, which again is the same as the mean, is each number times its probability, so x sub I times p sub I, added up. Or put another way, it's 0 times 0.05 plus 1 times 0.28 plus 2 times 0.19 plus 3 times 0.32 plus 4 times 0.16. And you can work that out. To find the variance, the variance of x is the sum of each number minus the mean, that's the thing we just found in red, squared times its probability of happening. So the way that looks is, we'll figure out what that is in red in just a second. In fact, let's see, if I work that out, I get 2.26 is what that works out to be. So I'll write that on there. This is 2.26. So then this in green is going to be 0, that's the first number, minus 2.26 squared times 0.05, plus, I'll draw it underneath it, 1 minus 2.26 squared times 0.28, plus 2 minus 2.26 squared times 0.19, etc., etc. Now I want to show you a slightly or somewhat quicker way to do this if you don't have to show any work. So I need to put these numbers into my calculator into L1 and L2. Clear out what's there. Type them in. So this is 0, 1, 2, 3, and 4. And then these numbers here, which of course we'll need to add up to 1, go right here. So I got them in L1 and L2. I'm going to go to my home screen and press Stat Calc, and it's 1var stats, where the numbers are in L1 and the frequency of those numbers are what's in L2. Calculate, chicka chicka whir whir. This here obviously is the mean that we did in red. Now this number right here is the standard deviation. So if I take that number and I type it in my calculator, can't write it right there, into my calculator, 1.171494772, and square it, that's the variance. That's the variance right there. Let me get rid of this thing. There we go. There's the variance, 1.37. That's what I would get if I worked all this out in green. 1.37 is the variance. And then this number right here is the standard deviation. Moving on to 107, before I can use rules for variances and sums and differences, I must make sure that the variables are independent. Now again, this is only for variances or standard deviations. The law of large numbers says if I look at a probability thing over and over and over, what I call bucket full of times more, my samples data will get closer and closer to the true mean, or the true number. Now, that doesn't mean it gets closer in the short run. So I believe that coins that are balanced give me 50% heads and 50% tails. If I flip it 10 times, I might be 50-50, I might not be. But the more times I flip it, 5 times, 15 times, 50 times, 5,000 times, 5 million times, I'm getting closer and closer to finding out the true value. That's the law of large numbers. Number 109 says, for test 1, we had a class average of 80, standard deviation 10. For class 2, class average 70, standard deviation of 12. What's the mean of the two tests added together, and what is the standard deviation? So first of all, the mean is going to be adding them together. Mean of x plus mean of y, which is 80 plus 70, which is 150. Now, the only way I can find this is if they're independent of one another. So if independent, then I can find the variance of x plus y by finding the variance of x and adding it to the variance of y. So my standard deviation here is 10. That means the variance is 100. There's a squared in there. And the variance here is going to be 144. So this is 100 plus 144, which is obviously 244. That's the variance if they're independent. So I can come on my calculator and find the square root of 244. That's the standard deviation, 15.62. So the standard deviation of x plus y is 15.62. Now it says find the mean difference. I can just subtract which is 80 minus 70, which is 10. And again, if I'm going to do the standard deviation of the difference, I've got to have independence. But if they're independent, the standard deviation of the difference is the same as the standard deviation of the sum. So same thing I did before, 15.62. On number 111, if I cut the scores on test 2 in half, so I take this 70 here and I cut it in half, and then I add 50, that's the new average, 35 plus 50, which is 85. What's the new standard deviation? Now, all I have now are test 2 scores, so there's nothing to worry about with independence. So I'm looking for the standard deviation, which we're going to find it with variance, of 1/2 of y plus 50. Now, the 50 doesn't change anything, so it's just the same as the variance of half of y, which is 1/2 squared times the old variance of y, or 1/2 squared times 144. So I'll grab my calculator and go 1/2 squared times 144. That's my new variance. So my new standard deviation is the square root of that, which is 6. Now some of you guys will correctly note that that's just half of my old standard deviation, and you can absolutely work it out like that. I prefer to work with variance. So number 112, I multiply test 1 by 2 and subtract 80. The new mean then is going to be 2 times 80 minus 80, which is going to be 160 minus 80, same as the old mean. And the new standard deviation is going to be the old standard deviation, and this part of it I don't care about. So we'll use the thing we just discovered. I can just multiply the old standard deviation by 2 to find my new standard deviation times 2, which is going to be 10 times 2, 20. That's my standard deviation of my new problem, which is 2x minus 80.